and you can look at these collisions between the two different populations or with themselves. And in addition, there is a dynamical friction contribution because there's an attempt to get to energy equipartition, and there's a recoil, and you can equate those, and then you can work out the collision enhancement factor resulting from the difference in the velocity dispersion. And the general idea is that when you have relatively massive object comes through here, and then their velocity dispersion is actually absorbed by the field planetesimals. As a result, they tend to have a runaway accretion because that their cross-section is larger. But when they become relatively larger, start to greatly excite the neighboring planetesimals, and they become an oligarch because the velocity dispersion can no longer be kept small of their feeding building block material, even though their own velocity dispersion is small. This is referred to as a oligarchic stage, and then eventually they will tend to empty out most of the material within plus minus 5 Hill radius on each side, and this is commonly referred to as the feeding zone. You may recall I worked out this square root of 12 times the Hill's radius if you start out with a circular orbit. But in the presence of gas, generally these things eccentricity tend to be damped, and so you get a little extra, but not much. And so this, when you empty out all of the material inside this region, and then these planetesimals, or these embryos, start to become dynamically isolated from each other, and you reach what is called the isolation mass. To go any further, you need to increase the eccentricity or increase the surface density. Okay, so now here's worthwhile to talk about. So far, I only talked about impulse approximation, but in principle, you should think more in terms of things like these long-term interaction, namely secular interaction. The secular interaction cause things to perturb each other, and their eccentricity goes up and down. You can write the eccentricity of two bodies in terms of their ratio and the relative longitude of periapse in terms of their difference. And then you can reduce the complexity of this linearized set of secular equation down to something very simple, namely the ratio of the eccentricities to the relative angle, and you can see immediately there are possibilities of what is called libration, namely this angle is limited to a narrow range, or circulation, and they go all over the place. Now, so as long as this is to the first order, that all of these things are, the energy is conserved. But the moment you go to the next order, and energy is not. Okay, so remaining in the first order, you can then add up not only three particles, you can add up fourths, fifths, and sixths. You can add additional contribution, such as contribution from relativity, or you can add in forces due to tidal friction and many other things. Okay, so I mentioned orbital elements. A very important orbital element is really this thing called the Runge length vector, because it contains information about both the magnitude of the eccentricity and the direction. And you can write down these type of vector, and you can go through vector analysis and to look at their time-dependent evolution in terms of various vector equations. And you can do orbit averaging. Once you do orbit averaging, you can start to reduce the complexity, and you evolve things on the time scale of secular time scale, which is quite long. For the Jupiter-Saturn interaction, it takes place, 600,000-700,000 years, something like that. Anyway, so So you can not only orbit average the inner one, but you can also orbit average the outer one to get things like feedback effect going back and forth. Don't worry about these equations, and they're just to show that you can do it, okay? Now, what if you have 8 bodies? In the solar system, we have 8 bodies, and then the 8 bodies, they're all interacting with each other. To the first order, you can get a set of normal modes, and these modes have certain eigenfrequency, and the contribution to these different eigenfrequency is dominated by various planets. For example, you can have things like the nu 5 is dominated by Jupiter, nu 6 is dominated by Saturn, and you can get these special locations where the interaction between Jupiter and Saturn can perturb each other with a precision, and that can cause strong resonant perturbation at somewhere else. Okay, these are known as secular resonances. Okay, now people often talk about cosine effect, which is related to some extent, and is again these type of secular interaction, but now it's involving not only the eccentricity, but also the inclination, and also the longitude of ascending node. I'm a very simple-minded person. I look at this very simple set of linearized equation given by Mikolo. What's his? Finn and Seppo Mikolo. Yeah, sorry. Actually, Yinan was Kim Yinan was here. But anyway, this is commonly referred to as a cosine mechanism, cosine effect, simply because these things are proportional to cos I. And so you can see from this, you can actually get into a log resonance, and you can get very large amplitude if their initial eccentricity is large. Of course, one can go to next order, and one can include other effects, and I think Scott will talk quite a bit about this. Okay, let me go on to talk about what if you have all these secular interactions, what eventually will happen. And if you expand to the next order, you start to get into also interesting resonant terms, okay? And resonant terms, now this time, you now have to look on time scale comparable to the orbital time because the phase matters, okay? And these are the kind of resonance you can get in the Laplace resonance, and so on and so forth. And one can do lots of orbital calculation to look at the orbital elements as they change in time. So let me go on to talk a little bit about this long-term stability. Again, this is the area that various people, Yanqing and Norm and various people have looked at this at length. And you can expand this random length vector, and you can show that over time, over course of time, suppose I start out with a solar system, and I made the 4 planets or 2 Jupiter mass, and I can see that gradually, after about a few million years, they will cross each other's orbit. And what is happening there is that the eccentricity gradually increase, and they start to, this second order effects start to become important, and they start to give you a diffusion of this longitudinal periapse. And so some of the conserved quantities in the first order linearized equation no longer is preserved. And you get this diffusion process, and eventually after some time, and you can start to get relatively large eccentricity, and then they can start to cross each other's orbit. Rosemary Marlin did this, and then you can have these, when they fill out these resonant widths, and they start to go into other resonances. Now, this is like a circuit with 3 jugglers, and each one is at their own pace, and then they start to perturb each other when they have so many periods to work with, and they start to overlap these resonances. When they do that, they start to diffuse into this region. You can get orbit crossing, and in fact, this is something that I thought about very deeply, like Poincaré. You can do this with n number of bodies, and you can calculate from this type of semi-analytic interpretation of numerical results. You can work out things like the crossing time of the orbits as a function of normalized spacing, normalized against Hill's radius. And you can see that in the presence, in the axis of gas, and if you go too far away, then these time scale becomes very, very long. And you can do this for 3, 4, 5, 6, 7 bodies. Here is 7. This math ratio can do -7. So it doesn't really matter because it's already normalized. Now, in the presence of gas, the eccentricity can be damped, so this crossing time is still very long. The moment you pull the gas away, they can start to cross each other's orbit. And after some relaxation process, you can then produce the radius eccentricity distribution. Having worked on this for a while, and we now can try to use the spirit of the Monte Carlo method in stellar dynamics. We can do similar things with planetary systems, including these long-term relaxation process, and we can start to try to reproduce things and match them with numerical simulations of various sorts, looking at n-body systems, look at things like eccentricity distribution as function of radius, and so on and so forth. And we can even take into account the possibility of resonant capture, and we can incorporate all of this into what is called a population synthesis type of code, which is no different from the Monte Carlo type of simulation in stellar dynamics. You can start to try to map out things like phase space distribution for various physical effects that you put in, trying to explore the possibility of phase space distribution. Okay, so now I'm going to talk a little bit about dissipated process. Okay, so I talked a little bit about collisional dynamics and coagulation and fragmentation, sticking probability. I won't go into all the details and like what I had done before. And so I'll talk a little bit about this because coagulation process and collision process is turned out to be important in the context of planetesimal growth. But it may also be very important in the context of star formation. The cloudless cores may indeed collide and coagulate, and it is also possible that even stars may collide and coagulate in galactic center. So these are relevant type of problems, and okay. Now, you can either do these things in a dynamical manner or summarize them in terms of a coagulation type of equation, which basically evolve. It is kind of like some moments of the Boltzmann equation, except you focus primarily on these the distribution function of the size, but you include things like collisions and fragmentation in terms of probability functions, and you can derive these type of probability functions because in planetesimal disks, when things collide greater than tens of meters per second, and they will break up each other, but you can include this type of effect in this. And this has commonly been referred to as a kilometer-sized barrier, because when they grow to kilometers in size, the collision speed tends to be larger than tens of meters per second, and they tend to fragment. I will offer a solution for you a little bit later. Okay, so I also want to talk not only gas dynamics is important to the stellar dynamics and particle dynamics, but radiation feedback is important, and especially in the context of solar system. And for small grains, you can have the beta force, radiation pressure exerted from the central star. You can have Poynting Robertson effect, and that's also important. And in addition, even in the asteroid belt today, we can have things like what is called the York effect, namely that if different side of the asteroid has different albedo, and then you can actually have a process of spin up, and then give you a radiative feedback torque, and that can cause things to spin up. And the spinning asteroids can radiate more in the afternoon than in the morning, and therefore, they too can give out this momentum transfer and cause their orbit to change. Now, this is particularly important in the context of asteroids today. But around extrasolar planets, because they are 100 times closer to the sun, in fact, their period is 1,000 times shorter, and therefore, that the actual physical size that gets affected is a few hundred times larger. And so if you have residual planetesimals in here, and that planetesimal, not planets, but planetesimals can get affected. So if you have lots of residual planetesimals, they can actually push larger objects around. Tides. Let me talk a little bit about tides. I'm going to separate tides into two different parts, for collisionless stellar systems and for a system where there are some gas. Okay. Now the main difference is that if you look at collisionless systems, we have plenty of evidence of tidal disruption, and by looking at tidal debris around globular cluster, and we can look at these Sloan data, and you see streamers all over the place. Seems to be evidence of lambda CDM and disruption of some incoming dwarf galaxies, and you can do this kind of thing. And then we can also look at things like open cluster. Okay, if we look at open cluster, and which is computationally less challenging because there are only a few thousand members, and but you do need to take stellar evolution into account in a big way. And then what you find is that from the observational motivation, that you count out the number of clusters in the nearby region, and you estimate their age, and you see there's a sort of fairly flat type of that distribution, which has been interpreted by the disruption of some of these clusters as they age, and the ones that can hang on the longest are the most massive and rich systems. So nearly all of the stars are forming clusters, one sort and another, and this is also important for the context of planet formation, because our own solar system presumably formed near a massive star, because we see the presence of these radioactive, short-lived radioactive isotopes. And so this kind of massive stars are only found in relatively rich systems. So if you want to trace back the history and you want to understand the galaxy as a whole, what type of planetary system you should have, you need to understand this tidal disruption of cluster problem. Okay. Now, tidal disruption of globular clusters versus dwarf galaxies. Globular clusters are closer, but they're to the galactic center, and but they are much more compact, and they undergo two-body relaxation to refill the region of near the Hills radius, and they tend to have replenish that region, and that region may give you a velocity dispersion that indicates that two-body relaxation comes out here and then isotropies in the outer region, whereas in dwarf galaxies, there are very few, well, they're 10 times less massive, and when the stars get to the outer region, they tend, the relaxation time scale is much longer, and they're much more loosely bound. They have a tendency to get disrupted. So this may be the reason when we look at things like Fornax dwarf spheroidals, we see inside Fornax dwarf spheroidal, there are 5 globular clusters. If you use the standard dynamical friction formula, these globular clusters should sink to the center of dwarf spheroidals, but instead they are preserved for the age of the system. And one way to do that is if it loses some mass, it's called shaken out somewhat. But in the center of clusters of galaxies, we often see things like nucleated dwarf galaxies, and they may very well be the byproduct of globular cluster that's sunk into the middle. Another form of tidal disruption is this type of concept on a much smaller scale. Instead of taking a stellar cluster, you take a binary. And you get into the neighborhood close to a black hole, and then during that close encounter, one star may get into close to the black hole, the other one can go out. This is known as a Hill's mechanism, and this has been suggested as a primary mechanism for forming hypervelocity stars. Okay, so now let's put in some gas. If you put in some gas, then what happens is that this region, when material is lost, the relaxation timescale for the gas particles is relatively short. They get replenished, and so then they can go out of the Roche radius. We see gas streams, such as the Magellanic Stream. Along the Magellanic Stream, we don't see many stars, but we do see this gas stream. It could be due to ram pressure stripping, but it could also be due to tidal interaction of this kind. And by looking at the dynamical orbit and looking at the phase space distribution or the velocity distribution here, you can reconstruct the potential of the halo and perhaps even the buildup of the halo. And there's some degree of uncertainty because NFW only is good for the inner region of the galaxy, even from their Millenian simulations, but for the outer region where the Magellanic Cloud venture to is still an open question. There's also something Shang Fei had done by looking at the 2 planets which undergo an encounter, and if it goes through this kind of encounter, and then there could be a little bit of tidal disruption here, a little bit of mass loss, and while the planet with a core can still go out there, but this can change the semi-major axis, and it can change the mass content of the system, and eventually you can either kick the planet out of here, or you can cause substantial amount of mass loss, and this type of phenomena has been pointed out here by Murray and Wu and Murray. Okay. So this type of process, the outcome may lead to an evolution in this type of phase space. Now, here again, I'm talking about also a binary star in the AGN disk. Okay? If you have a binary star in the AGN disk, as they move around, they tidally interact with the disk, and this can cause them actually to spiral towards each other, and that spiraling towards each other enables them to transfer also some mass onto them. They may be able to accrete some mass onto them, and as a result, one of the 2 binaries can become a supermassive star, or can be a massive star, and then they can explode and giving contamination to the disk around the AGN. Pablo had done some of this, and Klein and Barreto had looked at this problem as a possibility. Binary breaks up, and one of the components can also escape as a hypervelocity star. Planetary spin is interesting because we know tidal, from the solar system dynamics, we can actually work out things in this, which is called the equilibrium tide, and try to look at the distortion. and try to see how it can lead to synchronization, and we can hide all our ignorance in terms of what is called this Q value and the Q prime value. Now, that is really a dissipation mechanism, and but you can work this out. And now we have the opportunity to do some of this stuff and to actually try to measure this Q value for extrasolar planets. For Jupiter and Saturn, this quantity is thought to be somewhere around 10 to the 5. But for extrasolar planets, what you could do is that if they become tidally synchronized, their spin will become comparable to their orbital period, which is a few days to a few weeks to a few months. And that is much, much longer than the spin period of Jupiter and Saturn. So therefore, the planetary body will become spherical. Now, if you still see a planetary body which is rotationally flattened out to some period, then you can determine this Q value. You will see this result in a few weeks. And then there's tidal circularization, okay? And similar type of effect can also lead to the circularization of the orbit, and this time the dissipation occurs in the companion, and mostly due to a moon or something like that. And then you can also work out this type of process, and this may indeed be the reason why the short period planets tend to have nearly circular orbit, where the long period systems may not. Okay, gaseous environment. Okay, I'm trying to rush, try to finish. Okay, segregation due to interaction and non-interactive matters. Okay, here non-interactive means not physically interact, but gravitationally still interact. Things like dark matter, stars, and this is like gas. Okay, so you already know things like the bullet cluster, and this type of process can give you a segregation of gas and dark matter. And in the context of globular cluster, one interesting idea and is that if you look at globular cluster today, they have no dark matter, and they're chemically, by that I mean in terms of iron, they're very homogeneous, and that process could be due to the fact that they have been gone through Cloud collision, and then the dark matter and previous generation of stars may have flied out. Okay, this is also important in the context of self-contamination and the retention, of mass loss due to stellar evolution in stellar clusters. Here, whereas you can see this separates the gas from the stars and dark matter, here you may be able to retain it. Now, one possibility that people are already finding is that in the context of stellar clusters, they can now look at other elements, light heavy elements, and the light heavy elements seems to have a variation, and not only in terms of the color magnitude diagram, but their position relative to within the cluster. And this could be due to the retention of some of the material that is shot up from stellar evolution. But if it occurred very early, I'm sorry I couldn't put this up in time. This is time, okay? Now, if you do it very early, then most of the material that comes out in the form of supernova. So they will blow out of this region very quickly. But if you do that at a later stage, when most of the returning material is from red giant, and then you can actually retain to perhaps form some second generation of stars. Okay, now I haven't talked about everything, but I'm running out of time last night. And here is the evolution. Okay, so in the context of, why am I doing this? Okay, star formation efficiency. Okay, when you have gas that leaves the system or in the presence of other stars, and they may also change the potential of the star cluster, and you can lead to perhaps with a dissipated process, you can lead to initial mass segregation, and you have mass loss from stellar evolution. And this may also be related to some issues concerning the biggest proof against lambda CDM, the so-called too big to fail problem for the dwarf galaxies, and finally maybe lambda omega for the galaxies. Now, so let me just touch on some things. And I said that in this Pipe Nebula, and Charlie Lada has observed in Pipe Nebula some sort of initial size distribution for cloudless cores, and they look remarkably similar to the IMF of young stars, as Krupa described it, or Chabrier described it, but the peak is shifted by perhaps a factor of 3. Now, one question is, why is this IMF so similar? There are many reasons. One of the potential reasons is that these cloudless cores, in fact, undergo coagulation, and in the process similar to what I talked about in terms of planetesimals. And if that happens when you form two-phase medium, and they can go through this, and you can see that from these calculations, you can indeed evolve into this type of system. Okay, let me move on. What about the dwarf galaxy problem? The dwarf galaxy problem is that in lambda CDM, C means cold. Okay, so the system starts from small because it's cold. It builds up small at early stage of the universe, and when the universe is dense. So therefore, these small dwarf galaxies have high density, high phase space density, and so when they merge into the larger entities, they tend to be more resilient to tidal breakup. So they preserve their entity, and in fact, the lambda CDM crowd used to say there's a missing satellite problem. And I think it takes a cosmologist to be so confident that when nature does not agree with their result, it is nature's problem. Okay, so anyway, in this lambda CDM challenge is that from the simulation, Millenian simulation, you tend to get objects which are pretty big. They're too big, so that's why they're referred to as too big to fail. But when we look at the dwarf galaxy in the Milky Way, the neighborhood of the Milky Way, we find that their velocity dispersion is much smaller, and they have not only less velocity dispersion, namely less dark matter, but they have even less baryonic matter. So how do you do this? The total amount of baryonic matter is not that much. Okay, it's even in the cosmological baryonic number, it's only about a few, little over 10%. So how do you do this? Now, one way to do this, you remember I talked about the collapse calculation. During the collapse calculation, if along the collapse, okay, when they start to collapse into this singularity or the central dense region, okay, and their velocity is almost parabolic. So that means that the total energy of individual stars is small compared to their kinetic energy and potential energy. Just like what Changfei said, found in his simulation, if you lose a little bit of mass near the turnaround point, okay, it will make a lot of difference. Okay, so because this mass, if it's lost through supernova because of star formation process, and then the bounce factor when you come back will be considerably less than what it used to be. So to think virialization will always give you a factor 2 reduction in the half mass radius. It's thinking only in terms of stellar systems. But if you have gaseous system along with it, you can actually try to resolve this problem. Okay, so now disks. This is my favorite. Okay, so now disks plays a major role on the gravitational interaction for any entity that it exists in it. The simplest one is that due to dust to gas drag, and because the gas in this disk rotates around slightly less than Keplerian velocity, simply because it's hot here and colder here, the pressure is higher here, lower here. So there's a pressure gradient, and that causes a sub-Keplerian orbit and a dust particle that is big enough to segregate from the gas will start to feel a headwind, and they will slow down and spiral in. A lot of people have done this. Pablo did this. Pascal did much of this. And this process can cause things to migrate in. Okay? Now, we want to get around to this problem, otherwise all of the heavy element will get into the middle. There have been a lot of proposals for this, including things like, you know, formation by streaming instability, by vortex, by various other things. But if you can stop it, if you can manage to stop it at some location, which I will describe a little later, and then you can start to get in those regions of pressure maxima, you can actually reduce the relative speed between these particles, and you can somewhat reduce the collision fragmentation probability. But more importantly, that these dusty disk particles will settle towards the midplane, and they will try to roll in some way. Okay. Now, if they can settle, if they can accumulate and settle, if the surface density of the dust to gas ratio start to approach unity, then you can start to introduce gravitational instability, and this requires a mutual interaction between the fluid and the dust. What happens on a larger scale? I'll come back to you a little bit later on how do we stop all of this process. Okay. The next thing is something that I think familiar to almost everyone in this room. It is this interaction of an embedded object inside a protostellar disk, and if its mass is relatively small, it can actually excite spiral density waves, and by exerting what is called a Lindblad torque, and then there's also around this horseshoe region, you can get a co-rotation torque. In general, this co-rotation torque, in the absence of viscosity, will get exaggerated, namely that it will get weakened because the fluid will turn around here and it will cancel each other out, and you get a net zero torque. However, if there's viscous evolution in the disk, material can replenish in this region, and you can maintain this co-rotation torque. And the co-rotation torque can be both positive and negative, and you can write down this the torque from the linear formula that is right here and multiply by a coefficient. And then you can look at the disk structure, and then you can calculate what that coefficient is. And that coefficient is a function not only of the semi-major axis of the disk, but also the mass of the planet. And then in some region, it's non-exaggerated, other regions are exaggerated. And generally speaking, in regions which the disk is viscously heated, then there is a possibility of outward migration in regions which is irradiated, primarily heated by irradiation. They are primarily going inwards. So what I want to say, in fact, is that the place we're going to stop particles from going in could be anywhere here, could be the ice line, but the most robust place they will be stopped is near the inner boundary, near the magnetosphere disk interface. And this region, material will pile up, and the grains will stay here together. Even though you may start to build up objects that is surpass kilometer in size, their fragment never go anywhere. They will just keep on piling up. It's kind of like last winter when you have snow on top of snow on top of snow. Eventually, the roof will collapse. and you get gravitational collapse, and they can then start to grow further and further because you have continuous supply of material. Isolation mass is not an important issue here. Eventually they become sufficiently massive, they can turn around and go out. Okay. Now this may account for the robust formation of super Earths. That's why we see super Earths everywhere. And as you go out, and relatively small object can get cleared away, and some large objects, because as they go out, they excite their eccentricity that cannot be damped effectively, so they may cross orbit, some of them get left behind. This may be the reason for diversity, that while many extrasolar planets have short periods, super Earths have short periods, the solar system has nothing inside the orbit of Mercury. And so we want to not only come up with a solution for the common existence of super Earths, but also to account for this diversity. So how do you then go from there to look at the emergence of gas giants? So here I looked at it, a example of cases. These are calculations done by Beibei Liu and also Xiaojia Zhang. And so what is plotted here is these migration of these planetesimals or embryos. Now these are different m dots, and these are different mass. Okay. Now what you see is that they're relatively independent of the mass, but if the m dot is relatively high, that these type of planetesimals can actually get squeezed together to come in to collide with each other. What is happening here? And this is a type of convergent migration, and if the surface density is relatively low, which corresponds to lower m dot, then they are actually, there is a resonant barrier. They're caught into these kind of mean motion resonance. They can't get any closer. But if their m dot is relatively high, you can get into this region. And this is only the hunting license for them to collide. And whether they collide or not, they have to go through many scattering process. Now here, the presence of gas is important. If you put in, in the absence of gas, when they scatter off each other, they will spread. Okay? But because in this region, there's a convergent migration, whenever they get scattered out, they will come back in again. It is like a half pipe for the snowboarders. And they keep on coming down to the valley, and sooner or later, they will collide. Okay, when they collide, and some collisions may lead to mergers, some collisions may actually lead to destruction. And so eventually, a few of them may build up to sufficiently massive cores to open up gaps, and some of these gaps are probably seen around photostellar disks, and they may stop growing thereafter. But during this process, because their mass is increasing rapidly, they can actually perturb the orbit around them. And when the mass becomes sufficiently high, that the accretion rate becomes very large, and mass doubling time becomes comparable to the synodic period. And at this point, you destabilize these orbits, and some of it will get scattered out, and some get scattered in. But there will be also some that will collide with these gas giants, therefore give you the metal enrichment in Jupiter's envelope and Saturn's envelope. Once you form the first one, you open up a gap, and then the stuff you scatter out, they cannot come back in quite at this location, so they will accumulate here, and through this type of result shows you that, and through this type of process, you can form multiple systems, not sequentially, but in a promoted, enhanced way. And this may even have the promising prospect of forming systems such as HR 8799. Okay, so these guys can also migrate under type 2 migration and eventually capture things onto resonance. And but now I won't talk about that anymore. Let me talk about the aftermath of planet formation. We have all these things that has eccentric, large eccentricity. They get excited, And then we have the presence of this gaseous disk. The gaseous disk, even though low in mass, but contributes to the non-point mass potential, therefore a precession. As the disk goes away, the precession rate decreases. The precession timescale becomes longer and longer, and then there is a secular resonance, nu5, that will propagate from here inwards. Along the way, it will actually clean out all the small particles and the large particles. The reason for that is because the secular resonance primarily excite your eccentricity. But the small and large particles, their eccentricity are damped by hydrodynamic drag and type 1 tidal drag, and as a result, they get cleared out. Okay, one of our students here, Xiaochen Zheng, has looked at this problem, and to show that in fact what you get left behind are the intermediate size asteroids, and hence this may provide the possibility of explaining the size distribution of the asteroids. This is also a mechanism, as is propagated into this inner region, to induce the formation of Earth and the late bombardment and the giant collisions between between the moon forming event. Okay, I'm just going to go quickly. Now, I mentioned about magnetic field. I should just mention that magnetic field does play an important role because it's a stopping location and for many things, but it also can cause the disk structure to change because it is due to MRI, but the MRI must be connected with some charge. So if you can stop this region near the central region, and you can accumulate, and you put all of these effects into account, you can look at the distribution, and then you can see that in relatively short time scale of tens of thousands of years, you can already start to form objects which are several thousand kilometers in size. Okay, so now the location of this is given by the standard formulas. But when the gas accretion decreases, when the disk depletes, the surface density will decrease, and the radius of this magnetosphere will increase. And if they do, and then what happens is that you have a type 1 migration gets stuck here, and as the cavity expands, it may actually go out. Now, this is maybe an important process because you can have the small guys reverse their migration. The large guys gets into type 2 migration inside, but the small guys gets here. Why is this an interesting problem? Because this may be a way to break the resonance which you start out with, because most super Earths are not in resonance. This and they're called speed effect, both combined together. Now, the magnetic field also interact on the close-in planets, and then the planets move in here. They can induce a unipolar induction, and we see this kind of induction induced by Io on the surface of Jupiter. And in fact, we can see a hotspot correspond to the footprint of the flux tube induced by Io. And we can also see one for Europa and Ganymede. And this type of process may introduce a spot which is probably have seen or been seen already around extrasolar planets. Okay. Now, in addition to that, you can also have torque, and that could cause the orbital evolution of some of these planets, because there's there's an orbital evolution of these planets, and simply because they're moving relative to the field, it induces an EMF, and this EMF causes a current to go through it. And if you go through this kind of process, in fact, this may be very important for heating up not only gas giants, but some super Earths. And here's one of these systems that may possibly be in the process of being fried. Okay, so I'm running out of time, so I just summarize a little bit about these, what I talked about. I haven't talked about many things. I'm just scratching the surface, but dynamical processes are important in the context of elliptical systems such as galaxies, active galactic nuclei, which I haven't touched on. I think they merit would do a lot of discussion there. And of course, Douglas Hickey will talk a lot about stellar cluster, and Scott will talk a little about planetary systems. So all the hard work I have already delegated to somebody else. And in the disk systems, and there are things like these galaxy spiral structures and active galactic nuclei in planetary system, especially what causes their diversity, what is the destiny, what should we be looking for out of these type of planetary system, what is the fundamental property that we should be looking at. If we're seeing that not only their ubiquity, but also their diversity, how do we characterize their general property? Okay, and there are fortunately a lot of forthcoming prospects on the ground. We not only will have continued operation of the Sloan survey and the HARPS and the CAT survey, and but on a larger scale, things like the BOSS and DEEP and etc. That will help us to understand dynamics in a linear sense on a larger scale, but on the smaller scale on things like galactic structure and things like planetary structure, we will be very much aided by that. And then for the planets, the WASP survey, which does the transit-based sort of, and then there are people who are also doing the Earth type of survey, transit survey, and this again is an area of rapid growth. And then of course there's time domain surveys, and which will give us things like microlensing events and many other things. And Palomar Transit Survey has already, factory has already produced some interesting results. Direct imaging from SEEDS and GPI, and they are going to tell us a lot more about existence of gas giants further out and their early evolution. Multi-wavelengths from ELMA will give us the sight, give us the direct opportunity to observe planet formation. That's an ongoing process. But perhaps the biggest potential boost is that we can look forward to in the next 2 years is Gaia. And that will tell us the whole kinematic structure of the galaxy, and it tells us a lot about stellar cluster and of course planetary system. And the transit surveys is now paused for a moment, but Kepler is not dead. It just evolved into a K2, and K2 of course is more difficult peak to climb, and but we will reach a new height. And followed by TESS, Cheops, and Plato. And then in terms of photometry, of course, we will have HST and JWST, microlensing surveys and all that. So for those of you who are contemplating about all of this field, you may have seen that I had my cliff-hanging moments, and this is a warning for you when you go to Niagara Falls. And I have actually been to the top of Victoria Falls, which is twice the height as Niagara Falls, and this area is called the Devil's Pool. I dare you to do it. Thank you. You mean I rushed too fast? I should have prepared some more.
I have one to get the discussion started. How much of it seems to me that there's a lot of work that's been done in detailed dynamics of planetary systems, and how much of it has actually permeated to the galactic and globular cluster communities?
Well, for the galactic is more difficult, simply because the time scale for the you only go around 100 times, so that the secular
effects are not important except near AGMs. Okay, so some of that work, I think Scott knows much better than I do, and that has been done quite a bit there. And I should say, as an advertisement of one of the projects, that the AGM disks is remarkably similar to protostar disks. It has every aspect of similarity. And in fact, the time scale is right. The fact that we have observed Popper motion within a few years tells you the dynamical time period is a few years. And the S star's age is few tens of millions of years. And their aspect rates about their physical size versus their distance from the center is about the same, 10 to the 4. And the mass ratio between the S stars and the central black hole is about the same as supers, which is about 10 to the 4. And they're in a disk. And in fact, one area that I have been thinking for a long time with Hubble and about this is using this type of process to actually to provide a way to get a starburst going. Unfortunately, or fortunately, the discovery of planets for 51 peg got in the way, and we had to put that on a hold since 1992. And but that is one area. Another area is a star cluster. I think star cluster is an interesting problem, and there the time scale is, in a sense, comparable to the secular time scale, and because you are, the characteristic dynamical time scale compared to the age of the system is in the tens of thousands and perhaps 100,000 time scale. The relaxation process is at play. And there are people who have looked at secular interactions and resonant interactions, and I am not really well informed that whether anything profound has emerged. But I think it is perhaps worthwhile to look at it, especially in the context of perhaps formation of intermediate mass black holes.
One more question. I would say that the actual connection between the planetary dynamics and the higher, larger scale dynamics, only relatively few people actually work on both of them and actually connect them. You can even find different.
They're all in this room.
Yeah. Most of them are in this room. And even we even have different names for the same things. For example, people use dynamical friction in case of for planetary dynamics in the disk, but in clusters, people would call the same thing mass aggregation. It's different things. Dynamical friction used the large scale is used for a different thing. They are of course all related, but even the names are not sometimes different. The tools, people like to use the same tool, but sometimes they don't use the same tool. They have n-bar discrimination in planetary dynamics and for clusters. Some of them fit only one of them, and some of them can be used for both and are not used. So I think much to do in connecting these fields.
Professor Truman.
Just to set some context, given all the tremendous pace of discoveries in exoplanets, can you tell me a successful theoretical prediction that's been made in the subject of exoplanets?
I know that you were going to say that. Okay.
I'm sure you have a good answer prepared.
Well, I should say, first of all, J.C. Adams was the first successful story, and Olivia.
Right? So planet formation.
Okay. Now, I think, in a sense, we haven't really departed very much from Laplace's original idea that things were formed in a disk. And most of the planets are in a disk. They are not formed like globular crystals. They don't have to be formed in a disk, but they're not like globular crystals. They're not like the elliptical galaxies, and Laplace was guided in a way by the observation of all of the